Hello, my name is Patrick Lambrix and I work at Linköping University and also part-time at the University of Gävle, both in Sweden. I was planning to talk about lessons learned for developing ontologies, but as we have the third day of this workshop, some people will talk about their experiences in the biomedical field. I decided to only focus on one lesson learned. We all know that developing ontology is not so easy. And here's an example of a possible categorization of animals, which we find in a book by Borges. And animals are divided into those that belong to the emperor, embalmed ones, those that are trained, suckling pigs. So nothing that is so interesting for current day biologists yet. There are also mermaids and fabulous ones, stray dogs. Those that are included in this classification, yeah, that's great. Those that tremble as if they were mad, innumerable ones, and now we're counting. Those drawn with a very fine camel's hairbrush, so pictures are fine. Others is never good to have in an ontology because its semantics will change. But if you write others, I would expect that that's it, but no. Those that have just broken a flower vase and those that resemble flies from a distance are also added. Then classifications can be cultural dependent. Here's a classification in Dirirbal, a language spoken by Aboriginals in Queensland, Australia. When they say that something is bi, it can refer to man, kangaroos, possums, bats, most snakes, most fishes, some birds, and so on. Balan refers to women, anything connected with water or fire, bandicoots, dog, platypus, echidna, some snakes, but not the bi ones, some fishes, but not the bad ones, and so on. So developing ontology is not so easy, and we are going to make mistakes. And dealing with these mistakes is the topic of this talk. I'm going to talk about debugging, taking away wrong information, and completing, adding correct information. So there are different kinds of defects in ontologies. The most easy to find and also repair are syntactic defects. Could be things like wrong tags or spelling mistakes or incorrect format. More interesting and more difficult to detect and repair are semantic defects, which include unsatisfiable concepts. These are concepts to which no object can ever belong. So for instance, if we have the concepts dog and the concept not dog, and we combine them with an and, then we get an unsatisfiable concept because no object can be a dog and not a dog at the same time. Ontology that contains unsatisfiable concepts is called incoherent. When there are contradictions in your ontology, you call the ontology inconsistent. And from inconsistent ontologies, you can derive everything. Also modeling defects, and these have to do with whether you actually modeled what you wanted to model, while semantic defects were more about, is the logic correct? And examples of modeling defects are wrong and missing relations. So here's an example of a semantic defect, comes from the DICE ontology, where a brain is defined as something that is a central nervous system and a body part, and there are some other requirements. We also know that the central nervous system is a nervous system, and that body parts and nervous systems are disjoint. So nothing can be a body part and a nervous system at the same time. But it was defined that brains are central nervous systems and thus nervous systems and body parts. So which means that there are no brains. Example of a modeling defect. The Ontology Alignment and Evaluation Initiative is a yearly event where the performance of different ontology alignment systems are compared. In the anatomy track, 2 ontologies are used related to anatomy, one about mouse and one about human, both about 3,000 concepts. And in this task 4, partial alignment was given with 988 mappings. Now, from this information, you could actually easily derive that 121 isolations were missing in the first ontology and 83 in the second. I'll show you later how those are done. So ontologies with defects, which most of them are, they are of course useful, but they also lead to problems when you use them in semantically enabled applications. If you have wrong information, you may derive wrong conclusion. If there's missing information, valid conclusions may be missed. And here's an example of the influence of missing information. We are going to query PubMed, a big database of over 30 million abstracts in the field of biomedicine. We are going to query PubMed with scleral diseases, and we want to get back the abstracts that are about scleral diseases. Now it's going to use MESH, which is a vocabulary. And in MESH, it says that scleritis is a scleral disease. So it will take into account this and therefore also give us all the documents about scleritis. And in a query that I did some time ago, 1,663 articles were returned. So what happens if this is a relation was missing? Well, then only 948 articles were returned, which means that we missed quite a few. So how can we complete and debug? Well, there are different stages. One is a detection state where we find candidate defects. Then we need a domain expert to validate whether these really were defects. And then we have a repairing phase where we remove wrong information and add correct information. Many systems nowadays actually don't use a domain expert yet, so they don't have a validation phase, but it also means that you cannot guarantee the quality. So how do we detect wrong information? Well, ontologies are pieces of software, so you can use the inspection method where you carefully go through your code and check whether everything that you wanted to model is there and whether the intended conclusions can be derived within your ontology. Most systems that deal with wrong information deal actually with semantic defects, and they're based on logical reasoning. So they would check for you whether there are incoherent relations. So do you have unsatisfiable concepts, and do you have an inconsistent ontology? For detecting missing information, there are many approaches. Inspection works as well. You can use ontology learning, ontology extension, ontology evolution approaches. Many approaches use linguistic or logical patterns. And an example of a linguistic pattern is animals such as dogs and cats. This may hint that dogs and cats are actually sub-concepts or of animal. Doesn't always work. For instance, cities such as Paris and London, there's another kind of relationship. You can also use knowledge as intrinsic in an ontology network. So here you have several ontologies with mappings between them. So assume that this is one ontology, this is from the other ontology. We have a mapping that says that these two are equivalent, these two are equivalent, and there is a relation here, then there should be an is a relation there, so this one is missing. And this is how we, this is the method that we used for finding the missing is relations in these anatomy ontologies. And there are also machine learning and statistical methods that can be used. So lots of work on detecting missing information. A system that I could recommend to use for detecting these kind of problems is OOPS. You can upload your ontology to OOPS and it will give you back a report. So it has a list of 41 pitfalls, as they call them, which are possible defects. And the system automatically checks over 30 of those. And here's an example of a report that it could give back to you. It's from an ontology that we created earlier. So here are things like it says that we created unconnected ontology elements. And it says it's a minor thing. Actually, in this case, it was not a problem for ontology. You may want to add annotations. And here it says these concepts don't have annotations. Also a minor thing. But then something that's important for reasoning is that there may be missing disjointness. And here it found something about missing domain and range in relationships. And this is also important. Not all of the pitfalls are actual defects, and that's why you will need to validate still on your own. But it gives you some good ideas about what problems could be in your ontology. So after having detected and validated your defects, you want to repair them. Essentially, what you do is taking away axioms from your ontology. And what you want to do is making sure that for the wrong information that you have in ontology, you remove information so that the wrong information cannot be derived anymore. And for the missing information, you want to add information such that the missing information can be derived. So I'm talking about this can be derived because usually you can do a bit more than just adding and removing. I'll give some examples. So here's an example from a biomedical ontology, which is about different joints in the body. And here we have detected beforehand that hip joint is a joint and elbow joint is a joint. These are missing in our ontology. So what we can do is, well, we could just add these, of course, that's the easiest way. And then these are derivable in our ontology. But we could also add something else, like hand joint is a joint, which is also true, and we didn't detect it before. Or we could add limb joint is a joint. And indeed, it's still the case that hip joint is a joint can be derived because hip joint is a hinder limb joint, which is a limb joint, which is now a joint. So we can actually derive this one. And similar for elbow joint is a joint, can be derived. Or we could add another one. Forelimb joint is a joint is also correct, but it will be redundant when we have added limb joint is a joint. So what we would like is systems that would propose us to add limb joint is a joint instead of the original ones, because the original missing isolation will be derivable. Plus we have added new knowledge that we didn't know about before, like limb joint is a joint, but even hand joint is a joint now. This we didn't know before, and forelimb joint is a joint. All of these are correct, and it's new knowledge. Now for removing wrong information, this is the brain example that I showed before, where brain was defined as a body part, the central nervous system. Central nervous system is a nervous system, and nervous system and body part is disjoint. So how could you remove this wrong information? Well, brain will not be unsatisfiable anymore if any of the crosses are removed. So if brain is not a body part anymore, then there's no problem for unsatisfiability because it doesn't connect. These are not connected anymore if this one is gone. Also, if it's not a central nervous system, there's no problem. Or if central nervous system is not a nervous system, also not a problem. So here you would like to have systems that allow you to find these possible ways that you could take away information so that the logic is respected. You do note that the main expert will need to validate because, for instance, you probably don't want to take away this one, that the central nervous system is a nervous system. So when we talk about detecting or removing wrong information, we talk about debugging, and when it is about missing information, it's completing or completion. Most of the current work focuses on one of them, but not both. And most of the current work is on debugging. Now, the remainder of the talk, I will just show a system that can deal with both debugging and completion. The system that we developed ourselves, we focused on the ISA structure, so missing and wrong ISA relations, but we also look at networks, so also missing and wrong mappings between ontologies. We have different versions for repos for the different knowledge representation languages. So depending on which constructors you allow in your language, like and, or, negation, existential, universal quantifications, and so on. And additionally, we also have a plugin for Protege, which allows you to do completion when adding concepts. More information about the different versions of the system and also what can be downloaded is available on the webpage that I show below. So here's an example for the validation phase. So the idea is that we have candidate defects here. And here we have a number of candidate defects that a user can validate. We show the candidate defects in groups of things that are connected. For instance, here are all possible defects. These could be missing isolations, or it could be wrong. And here we have clicked on this one, the brown one, and then the user can click on the question mark and say, yes, this one was missing, or this is wrong. The system thinks this may be a defect because there is a justification. So here it says why it thinks it was wrong. And it's because there was a mapping from bone to bone in the other ontology, and from jaw to jaw in the other ontology. And there was these isolations there. So it could be that this one is missing in the first ontology. We can also do completion. So here the missing isolation is actually hip joint in red here and joint there. And now the system is going to propose us two sets of concepts. And the idea is that whenever you use a concept in this set and a concept in this set, and you make an isolation from here to here, then this hip joint is a joint will be repaired. So for instance, if we would take lip joint is a joint, then of course, hip joint will be a limb joint and therefore a joint. So the isolation is repaired. And you can also do debugging. In this case, we have found, or the system has found, that cerebellum white matter is a brain gray matter, and this is detected as this is wrong. And this is because it went through the other ontology. So now the system allows you to look at these derivation paths and tell which ones are correct or incorrect. The system will also give some recommendations, both for the completion and debugging. And you can use existing information. The system will also derive all the conclusions of adding new information or taking away some information. So we'll give you some idea of why this is worthwhile. Here is a case where we just do completion. We have given missing isolations, 94 for MA and 58 for NCIA. And this is the same data set as before, but an updated one from 2013. And using this repose system, the 94 missing isolations from MA are repaired by adding 101 relations, of which 47 added additional knowledge which you didn't know from MA, NCIA, and the mappings between them. So this is completely new knowledge that you could find using repose. And similar for NCIA, there were 58 missing isolations were repaired by adding 54, of which 10 gave you completely new knowledge. Can you use this system when you don't have given missing isolations? Well, yes, you can. What we did was we used a biotop ontology, which has about 280 concepts. We randomly chose some isolation and removed them. We said, yeah, okay, these 47 are missing. And then we used the repose system, and these 47 which were missing were repaired using 41, of which 40 actually gave us additional new knowledge, which was not on the ontology before yet. Here's an experiment from the anatomy data set from 2010 again, where we have a network. So using the network, we found 102 missing isolations for the first ontology, 61 for the second, but also 21 wrong relations and 19 for the second, using the validation step in repose. Now for the new isolations, we added 85 for MA, which repaired to 102, which also gave us 22, which gave us completely additional knowledge, which was not in the network before. And for NCIA, the 61 were repaired by adding 57, of which 8 were completely new knowledge. Also 13 ISO relations were removed from the first ontology, 12 from the second, and also the reference alignment had mistakes, so they were removed 12 mappings. So if you want to know about more, if you want more info about debugging and completing, I would refer to this paper, Completing and Debugging Ontologies, State of the Art and Challenges, which is the most complete, the most recent overview of the field. And you'll find both discussions about methods and references to quite some systems. So let me end by thanking my co-workers, Ricard and Eva, our colleagues, Juan Yu, Mina, and Ying are my current PhD students, and Valentina and Zlatan were former PhD students. And Swedish Research Council, Swedish eScience Research Center, Swedish Agency for Economic and Regional Growth, and the National Graduate School in Computer Science have financed this work. If there are any questions, I'm happy to take them now.